Hello, everyone, and welcome to the GOCC, the Graduate Online Combinatorics Colloquium. Today, we have Sarah Bronner, who will be speaking about a Type B analog of the Whitehouse representation. But before we get started, I wanted to remind everyone of our community statement. This is a graduate online colloquium, and so we just wanted to keep three principles in mind. One, we are all learning. Two, everyone has something to contribute. And three, no one has all the answers, and that includes the speaker. So with all of that in mind, Sarah, the floor is yours.
Thank you. All right, let me share my screen. And thanks for the opportunity to talk. Can you see my screen, by the way? Okay, now can you see my screen? Okay, cool. And I'm sorry, I see some people in the audience that I know have seen this talk before. I'm sorry for the repeats, but hopefully you don't remember everything.
I don't.
Okay, so today I'm going to be talking about a Type B analog of the Whitehouse representation, and this is I finally finished writing this up, and it's on the archive under this number. Okay, so the big idea of this talk is that I want to take some really nice Type A story that brings together combinatorics in the form of the Eulerian idempotence, topology in the form of configuration space cohomology, and representation theory. And I want to generalize that to Type B. So this right here is the Type A story, and I don't expect you to understand what this is saying yet, because it's a lot of notation that I haven't introduced at all. But my goal of this talk is to explain what this picture is saying. So really tell you what this Type A story is in detail, and then tell you about my contribution to this sort of area, which is to generalize this picture to Type B. So I'm going to explain this picture and then I'll generalize it. Okay, so what I'm going to do is I'll first start with these symmetric group representations, which are called the Eulerian representations, and they have this property that they lift, which I'll explain. And then I'm going to interpret those representations topologically. And then I'll do the same thing over in Type B. So I'll tell you about the hyperoctahedral representations that I'm interested in, and then I'll interpret those representations topologically. Okay, so beginning with Type A, we really want to start with the descent set of a permutation. So here I'm thinking about a permutation of the symmetric group in one line notation. And the descent set of that permutation is thinking about indices where sigma I is bigger than sigma I plus 1. Okay, so for example, here are all of the permutations in S3, right? This is the identity, and we see that everything is in order. And so that tells me that in this case, I have no descents. If I go to the next permutation, right, I see that 3 here is bigger than 2. So that tells me I have a descent at position 2. Next permutation here, 2 is bigger than 1, but then 1 is smaller than 3. So that tells me I have a descent at position 1. And I could keep going. Okay, so this permutation has a descent at position 2. This one at the next one at position 1, because the 3 is bigger than 1. And then this last permutation is completely out of order, right? So 3 is bigger than 2, 2 is bigger than 1. So I have a descent at position 1 and position 2. Make sense? Okay. So this is a very classic statistic on permutations. And one really nice result that came out of it is that Solomon proved that I can actually define a subalgebra of the group algebra of the symmetric group by taking sums of elements that have the same descent set. And I'll call that algebra Solomon's descent algebra. So this thing that's sort of surprising about this is that it's closed under multiplication, right? So if I multiply two elements that are sums of elements of the same descent set, I still get something of that form. Okay, so let's see what this looks like in S3. So here are my 4 possible descents, okay? So I want to sum up all the permutations that have that descent. So in the case of the empty set, we said it was just the identity, okay? So here's my identity permutation. The descents that have the permutations that have a descent at position 1, we had 2, 1, 3, right? And then we also had 3, 1, 2. Okay, and so the important thing is that I have to take both of them together because they have the same descent set. And then, okay, a descent at position 2, we had 1, 3, 2, right? And then we had 2, 3, 1. Okay, and then this last descent set of both 1 and 2, we had only 3, 2, 1 alone. Okay, so my subalgebra is going to look like linear combinations of these 4 elements in the case of S3. Okay, so this is a sort of a really nice subalgebra, and a natural question that would come out of it is, can you find a family of orthogonal idempotents that decomposes that algebra? And so this is what Garcia and Rettenauer did. They defined a family of orthogonal idempotents. So that means when I say idempotent, I mean an element of the group algebra E, where if I square it, I get back to itself, okay? And so these idempotents, I'm not going to define them because it's super technical, but let's just take them to be E lambda. So lambda is a partition here. So they're indexed by partitions of n. And really the idempotents that I'm interested in are a coarser family that I get. I'm going to call them the Eulerian idempotents. And what I do is I'm just going to sum over these idempotents that have a fixed length. Okay, so I'm going to take a fixed length, sum over all of the lambda that have that length. So that means number of parts. And that gives me a new family of idempotents. And now I'm just going to have n of them. So from 0 to n minus 1. And here's what they look like in the case of S3. So it's not really obvious that they're even idempotent, but you can, if you stare at them long enough, you can convince yourself that they actually are, for example, in the descent algebra of S3 and idempotents. Okay. So I'm about to talk about representations of the symmetric group. So to make sure that we're all on the same page here, I'm thinking about irreducible representations as being indexed by partitions of n, okay? And when I'm talking about an irreducible representation, this is a lot of times how people write it. It's the spec module, but I'm just going to write the partition lambda. So for example, if I had the irreducible indexed by the spec module 2, 1, I would just write the partition 2, 1 here. Okay, so when I write a diagram like this, I really mean a representation of Sn, or S3 in this case. Okay, and so another thing that we're going to use is that the symmetric group has really nice ways of restricting and inducing representation. So in particular, what I want to talk about is the branching rules, where I restrict a representation from Sn plus 1 to Sn. And the way that I do it is I take this partition lambda and I remove boxes in all possible ways so that I still have a partition. So for example, if this is my representation of S3 and I want to restrict it to S2, what I'm going to do is I say, okay, well, I could remove this box or I could remove this box. And so what I would get is the sum of these 2 representations of S2. Okay, because those are the 2 ways to remove boxes. Any questions so far?
Yeah. So every possible way of removing a box from lambda, those would just be your bottom right corner boxes that you can remove, like.
Yeah, so it has to still be a partition after I remove the boxes. So I can't remove this box because then it would be like a skew partition, but it wouldn't be a partition.
Okay.
Can I ask a question about the previous slide, actually?
Yeah.
I'm not super familiar with the story. So can you say a little bit more of why we care about these orthogonal idempotents?
I guess they have a lot of combinatorial properties. I guess I would say that, so there's a nice special case, which is when k equals 0, then this idempotent, or the representation, I'll talk more about this, but the representation it generates is this nice representation called the multilinear component of the free Lie algebra. But generally, I guess I haven't motivated yet why these idempotents are interesting. But for me, the reason they're gonna be interesting is because I'm gonna think about the representations that they generate. which I'll say more about in a second. But I guess more broadly, they have a lot of nice combinatorics in type A, and then also can be defined for any Coxeter group and have connections to like hyperplane arrangements of those Coxeter groups and stuff like that.
Yeah, that's great. Thank you.
Okay. I'll motivate a little bit why I care about them.
Can I ask a quick question?
Yes.
For k equals 0, are you looking at, I guess on the previous slide, for k equals 0, are you looking at partitions of length -1?
Yeah, so the indexing is a little bit weird. I'm subtracting. So it's partitions of length 1.
Okay.
Did I write the indexing wrong? Maybe I want -1 here and k here.
Okay.
Yeah, I think, sorry.
Okay.
Good catch. Yeah, so it should, is that better?
Yeah, okay.
Okay, yeah. And this is really, the indexing here is really just annoying because you want it to match with other Coxeter groups, and it has to do with the braid arrangement having like rank n-1. Okay, so to answer Claudia's question a little bit more, hopefully, the part of the story about the Eulerian idempotents that I care about is that each idempotent is going to generate a symmetric group representation called the Eulerian representation, or the kth Eulerian representation. So here's how I'm going to do it. I take my idempotent and then I think about the ideal that it generates in the group algebra of the symmetric group. So for example, if we go back to this slide here and we look at this idempotent, we see that it's just an unsigned sum of every element of S3, right? And so if I multiplied any permutation by this idempotent, it would just rearrange the terms in my sum, but it wouldn't change the sum. So in other words, it would act trivially. And another way of saying that is the representation that I get for that idempotent is the trivial representation of S3. Okay, and then the other ones are a little bit harder to see. So when k is 1, we get this sum of representations, and then when k is 0, we get this reflection representation of S3 here. And okay, so two things. One is we have this nice special case when k is 0. This representation is isomorphic to what I'm going to call Lie-n, which is the multilinear component of the free Lie algebra. If you've heard of it, it's a very like nice, famous representation that has lots of cool combinatorics associated to it. And then the other thing I want to sort of note is that if we look at all of these representations together, we see that this is the regular representation of S3. And in general, I'm going to get some decomposition of the regular representation of Sn when I look at these representations. Okay, so what I've described so far is that these are representations of Sn. But it turns out there's actually a way to encode these Eulerian representations in Sn+1. So to formalize that idea, I'm going to say that a representation V of Sn has a lift to Sn+1 if I have some Sn+1 representation, let's call it W, such that when I restrict from Sn+1 to Sn, I get exactly V. So the way that I think about this is like W has all of the information that V has, and then it has some additional information as well. So a preview of what I'm about to say is that these Eulerian representations that I just described to you have a lift to Sn+1. Okay, so to get at this lift, what I'm going to do is I'm going to use the Eulerian idempotents to define idempotents in one higher symmetric group. So I take my item, and this is work of Sarah Whitehouse. So she showed that I can take these idempotents, these Eulerian idempotents, and for each one, I'm going to multiply it by some element of the group algebra of Sn plus 1, in particular, a sum of powers of an n plus 1 cycle. Okay, and it turns out that that product actually gives you an idempotent that lives in the group algebra of Sn plus 1. So it's not obvious that that's true, but it turns out it is. And she said, okay, well, those idempotents generate representations of Sn plus 1 in the same way, where I'm just thinking about the ideal that they generate in the group algebra. Okay, and we'll call those representations the Whitehouse representations. And then she showed that those representations exactly restrict to our Eulerian representations. So in other words, these Eulerian representations have a lift to the Whitehouse representations. Okay, so this is very abstract. Let's do an example here. Okay, so here are S3 Eulerian representations. And I want to think about what are the Whitehouse representations of S4 that restrict to each of these. So we're going to use the branching rules here. Okay, so let's start with this one. So I want to think about a partition of 4 that if I can only remove one box, and the box I remove gives me this. So it turns out the shape has to be this. So the trivial representation of S4, because this is the only box I can remove, and that gives me this partition. Okay, the next one, k equals 1. The partition that I end up getting looks like this, right? Because I could remove this box and I would get this partition, or I could remove this box and I would get that partition. Okay, and then the last representation here to get to restrict to this one, it turns out that what I need is this 2 by 2 box because I can only remove this last box here. Okay, questions about this?
I just want to,
oh,
sorry.
Go ahead.
You go first.
No,
Well,
no.
I
Go,
just
Claudia.
wanted to confirm that. So comparing this with induction, if we want to induce a representation up, we're looking for like all the ways of adding a box that has like, so then when we have a steel partition. And so this is not as, we don't get as much stuff as induction.
Yeah, exactly. Like, for example, if I wanted to induce this, I would get, like this plus this plus that, right? So it's like much bigger. Because I could add a box here, here, or here. Does that make sense?
Thanks.
Okay, cool. Mark, you also had a question?
I think I determined that I don't have a question.
Okay, cool. All right, so I want to sort of give a disclaimer here because I think the last example can be a little bit misleading. So even though this sort of worked very seamlessly, it's not true in general that any representation of the symmetric group has a lift of Sn, has a lift to Sn plus 1. So like, for example, this is a representation of S4, and you can like try and check for yourself. There's no way to write down a representation of S5 that restricts to this. Okay, so we don't necessarily have existence, and we also don't necessarily have uniqueness. So for example, this representation of S1, the only one that there is, I could lift it in 2 different ways, right? I could lift it to this, and then I remove this box, I get this back, or I could lift it to that, and if I remove this box, I would get this back. Okay, so we don't have existence, and we don't necessarily have uniqueness. Okay, so this is sort of a more subtle property than maybe the last example showed.
Yeah. Could you cover what's the rule for lifting?
Say that again.
What's the exact rule for lifting?
So there's not really a good rule. The rule is that if I find a representation that restricts to the representation that I started with. So there's not necessarily like a way to tell if you give me a representation of Sn without checking, like, does it lift?
Right. So how do you choose the representation? Like out of the possible representations, how do you choose one?
So like for these Eulerian representations, these are defined by those idempotents.
Right.
So so this is like sort of an extra property that they have. They were defined via those idempotents, but then it turns out that they also have this lifting property, but it's not obvious that they do.
So I think I have a
Mhm.
similar question, which might be the same question, but I guess if you start with an Eulerian representation, then it has this Whitehouse representation, but is that unique? Because in general, you're saying there's not uniqueness of the lift.
Yeah, that's a good question. So it's possible that these have some other lift that we don't know about. I've never seen anything to that effect, and I'll present soon some other results that are like a different way of seeing these representations. So it's possible that these Whitehouse representations are the only way to lift the Eulerian representations, but I don't know that for sure. So this is just some family of lifts.
Follow up. So do these Whitehouse representations show the direct sum type structure also? So like this Eulerian representation has the direct sum of representations.
Mhm.
Do Whitehouse representations have any?
Yeah,
Or are
yeah. So this is like sort of a small case. In general, we might have sums over here too,
Okay.
like bigger N.
Hi, Sarah. I have another question if you have time.
Yeah.
So these Eulerian representations arose from these idempotents that were not the finer Eulerian idempotents, right? So there are other idempotents that are finer than these.
Yeah,
that are
so
used.
these are, let me go back. Yeah, so these idempotents I didn't define, but you might be familiar with them because they're like, I think they're the same idempotents that, or like they're one choice. So, okay, if you think about these idempotents in the context of the Tietz algebra, they're like one choice of, I think they're the choice of the uniform section.
Yeah. But my question is, so these should also define certain representations of the symmetric group,
Yeah.
right? Is it known if those can be lifted?
That's a good question. My suspicion is that they can't, but I don't think we know that for sure.
Okay. So,
Lots of good questions. Okay. Any more before
I just have a comment. I think on the when you were showing the Eulerian representations and saying maybe they don't have, or they might have uniqueness, it seems like if you could go back to where you had the partitions. Yeah, here. It seems like the middle one would lift also to a 2x2 rectangle plus a 4x1.
I think so you're saying like this plus what?
Like a long 4.
Along like 1 1 1 1.
Yeah, 1 1 1 1.
Let's see. So this one I removed there and there. Yeah, I think you're right. Okay, so I guess we have confirmation that they're definitely not unique.
No, this is not a solution.
It's
if
not?
you restrict it, you get the hook twice. Oh wait, you said 4. Sorry. Yes, this works.
Yeah, so this works, but it's not the Whitehouse representation. Because remember, yeah, so that's a nice example. I should incorporate that. Because yeah, so these Whitehouse representations are defined, like they're being defined via idempotents as well. So this is definitely not the Whitehouse representation, but we see that it does lift. Okay. I'm going to keep going with a recap. Okay, so we started right with this combinatorially defined algebra, and then I told you there's this family of idempotents in that algebra, And those idempotents generate representations, okay? And then those representations have this interesting property that they can lift from Sn to Sn plus 1. But from what I've said so far, there's sort of no reason that you should understand or have intuition for why this is true. And so what I want to do right now is to sort of explain it from a topological perspective, which I think makes this phenomenon a lot more clear. Okay, so to do that, I'm going to think about configuration spaces. And in particular, I want to think about configuration spaces of R to the D. So here I'm thinking of that as the set of points x1 through xn. So each of these xi's I'm thinking about as living in R to the D, okay? And then I just require that they're distinct. So for example, let's say D is 2. So I'm thinking about points, distinct points in the plane. And N is 3. So I'm thinking about 3 points. Then this is sort of a moving image of my space where each slice of this picture is going to give me a point in my configuration space. So you see I have my 3 points here, and they can move around however they want. And when I take a slice, I sort of get their location at that time. They can move around however they want, but they're not allowed to cross into each other. So this should maybe look a lot like a braid if you've ever seen those. And this space is actually the classifying space of the pure braid group. So there are connections there. Okay, maybe an easier example is if I just look at the configuration space of R, let's say N is 3 again. So now I'm just thinking of points x1, x2, x3 in R3 that are distinct. So if I drew this as a picture, I don't even need a movie anymore. It's just going to be the complement of these 3 planes. So each of these planes is where 2 of my coordinates are the same. And so if this picture isn't familiar, if I project along this line where they all intersect, I get a picture that looks like that, which probably is familiar because this is the rank 2 braid arrangement. Okay, so in all of these cases, the symmetric group is going to act on my configuration space by permuting the coordinates. So for example, if I had this transposition 1, 2, it would act on this ordered pair by swapping the position of 1 and 2, x1 and x2. Okay, so this is sort of a very old and classic topological space. And a natural question is, what does its cohomology ring look like? And this was answered by Arnold in the case that D is 2 and Fred Cohen for all larger D. So here's the presentation. And I don't want to dwell on the details of it too much. I just want to sort of note a couple of things. So the first thing is that this presentation, if you stare at these relations long enough, even though I'm looking at R to the D here, the only spot where D is occurring is in these -1 to the D plus 1s. So that tells me that if the presentation only depends on the parity of D. So I'm going to get like an odd presentation and an even presentation. And then if you again stare at these relations long enough, you can convince yourself that because this generator lives in cohomological degree D minus 1, these relations are going to tell you that this ring is only concentrated in degree 0, D minus 1, 2 times D minus 1, up to N minus 1 times D minus 1. So there's like, in other words, N pieces of this cohomology ring and non-zero pieces. Okay, so we really understand this, this cohomology. A more nuanced question that we could ask is, what is the symmetric group representation structure on this ring? So the reason that we have that is because the symmetric group acted on this topological space. So in cohomology, that induces a representation, and we can see the action really clearly. So the symmetric group is going to act on this ring by permuting indices. So if I have a permutation sigma, it's going to act on my generator Uij in the same way that it would act on I and j. Okay, and so one sort of partial answer to this question of what does this space look like as a SN representation is that if I take D to be odd here, then it turns out this cohomology, the total representation is exactly the regular representation of SN. And this is not true when D is even. And so this should sort of, this is going to preview for us that this is the relevant case for us, because we really, we already saw that those Eulerian representations also decompose the regular representation. And I want to actually relate them. So here's the sort of connection. The connection is that there's an isomorphism of symmetric group representations, where I get each Eulerian representation is isomorphic to one unique piece of this cohomology ring of my configuration space, in the case that I take d greater than or equal to 3 and odd. So here's an example of that in S3. So the new information here, this I've already told you, right? These are the Eulerian representations we've seen. The new information is that they're actually also describing pieces of a cohomology ring. Okay, so this was originally deduced by a character comparison using the work of Hanlon and Sundram and Velker. And then later I proved it in the context of Coxeter groups. So this is maybe a surprising connection, but it's going to be really important to what I'm going to say going forward. Questions about this? Okay. So we already saw that these Eulerian representations have a lift, and now we see that they are also described by these pieces of a cohomology ring. And so you might ask, can we also describe the lifts using some cohomology ring of a topological space? And the answer is yes. So to describe it, I'm going to first fix d equal to 3. Okay. And then I'm going to think about SU2, the group. Okay. So this is the group of 2x2 matrices that have determinant 1. And importantly, it's homeomorphic to the 3 sphere. So here I'm kind of thinking about the 3 sphere as the 1-point compactification of R3. Okay. And so now I want to think about the configuration space on SU2. Okay. And this n+1 here this is a preview that I'm really working towards getting the Whitehouse representations. So somehow defining this configuration space is going to help me get the Whitehouse representations. So, okay, this configuration space, it's a set of points P1 through Pn+1. Now they're all in SU2, and I again require that they're distinct. But this time, because SU2 is a group, it's going to act diagonally on this configuration space. So in particular, if I have an element G, it's going to just act on a point by, diagonally multiplying. Okay. And actually the space that I'm going to care about is not this configuration space on SU2, but the configuration space mod that diagonal action. Okay, so this can look very unintuitive, but I think it helps if we think about what is a typical point in the space. So let's say n+1 is 4. So here's a typical point in my space. It's just a set of 4 points. But because I've modded out by this diagonal action, I can multiply through by P4 inverse and get an equivalent point, right? And so here's an equivalent point. And you can see that my last coordinate is fixed at 1. And the idea is that I can do this in general. So a typical representative of this quotient configuration space is the set of points Q1 through Qn, where here I'm requiring that Qi is not equal to Qj is not equal to 1. And then 1 as my last coordinate. So we can try and picture this. So I can't draw a 3 sphere, but let's just pretend or get intuition from a 2 sphere here. So what I'm basically saying is I'm picking n distinct points on this sphere, and I'm not allowed to pick the North Pole. Okay, and that's really what this space looks like. Okay, so there's sort of 2 important actions on this space. One is by Sn+1. So here it's sort of the natural, my points are n+1 tuples, so I can just act on them by Sn+1 by permuting the coordinates. Okay. And again, this is a preview for a Whitehouse representation somehow. But then I can also think about, I had this nice description of the representative of my elements of my space, right, where they have a 1 at the last coordinate. And so a very natural restricted action here is to think about Sn acting on the first n coordinates and then just fixing that last coordinate. Okay, and so somehow this is going to help me understand my Eulerian idempotence. Okay. So to formalize this, I really want to relate this quotient space to the configuration space that I already know is related to my Eulerian representations that we've already talked about. And so the sort of intuition for what I want to do here is I was thinking about points on S3 where the origin, or sorry, the North Pole is removed, but I might as well have stereographically projected and picked points over in R3 because in stereographic projection, you have to remove the North Pole anyway. Okay, so that's the intuition for what I'm about to do. What I'm really going to do is I'm just going to say, okay, these spaces, it turns out, define an SN equivariant homeomorphism where I take my typical point in this space, and what I'm going to do is I'm going to stereographically project my first n coordinates, and then I forget my last coordinate. Okay, and so the reason this is SN equivariant is because I said that that SN action was just permuting these first n coordinates, and I can do the same thing over here. It won't change anything. Okay, so the sort of upshot here is that this quotient space, the sort of advantage of looking at it is that it captures an SN+1 action on this configuration space that a priori we didn't know existed. So the SN action on this quotient space, that homeomorphism tells me it's exactly the same thing as the SN action on my original configuration space. But the advantage of thinking about the space is that it actually makes an explicit SN+1 action. Okay, questions about this? Okay. So sort of the upshot here is that when I move to cohomology, that homeomorphism is going to tell me that I get isomorphic representation. So really sort of the takeaway is that each piece of this cohomology of the configuration space is going to lift to a unique piece of this cohomology of my new configuration space. So this is an SN+1 rep, and this is an SN rep. Okay. Okay, so we already saw that these Whitehouse that lifts are not unique. And so we now have two different lifts of the Eulerian representations, right? We have the Whitehouse representations, and now we have these pieces of this cohomology of this quotient orbit configuration space. And so you can ask, are they the same? And it turns out yes. So this is work of Early and Reiner, who proved that each piece of this cohomology ring is actually describing as a SN+1 representation a unique Whitehouse representation. So it's sort of exactly what you hope would be true. In particular, it's this isomorphism in our picture. Okay, so we now have this complete picture. So on the one hand, we started with these Eulerian representations coming from the idempotence, and we saw that they could be described via the pieces of this cohomology ring. Okay, this of the configuration space of R3. And then we said they lifted to the Whitehouse representations. And now I'm saying those Whitehouse representations can also be interpreted as pieces of a cohomology ring. Okay, questions about this? All right, so now I want to sort of tell you about the type B analog. So here I'm thinking about type B as the group of signed permutations. So if you haven't seen this before, you can think about it. I wrote down a permutation in one line notation for the symmetric group. I'll do the same thing for Bn, but now these sigma i's can be positive or negative. And really, I think the best way to think about it is as a signed permutation matrix. So it's a permutation matrix, but I can have -1s as well as +1s. So for example, this is like a permutation in B5, okay? So this tells me that like 1 goes to 1, 2 goes to -3, 3 goes to 5, 4 goes to -4, and 5 goes to -2, which looks like that as a matrix. Okay. So my first goal is to give some analogy of this Eulerian representation lifting to Whitehouse representation in the case of type B. And so really what I have to do is I have to generalize this descent algebra that we saw at the beginning. And so there are multiple different definitions of type B descent. So one possible definition is by Coxeter length. And this is sort of the most well-known definition. And in this case, we get a descent algebra, we get Eulerian idempotents and representations. But the problem is that those representations actually don't lift to Bn plus 1. And for experts, they still have a nice topological description. So these Eulerian representations are actually defined by sort of a standard, what's called an orbit configuration space, which I'll say more about. But it's the space, let me zoom in, of x points, the cohomology of the space of points x1 through xn, where now I require that xi is not equal to xj, and actually it also. Okay, so there's a nice description, but they don't lift, so they're not going to work for this context. So what I want to do is I want to think about a different combinatorial description of descent. So this one is due to Montacci and Reutenauer. And here's how they define their descent. So I'm thinking about indices in the set 1 through n-1. And I'm going to say that sigma has a descent at position I if, okay, when I take the absolute value of sigma I, it's bigger than sigma I plus 1. And these sigma i's and sigma I plus 1 have the same sign, or they have opposite signs, okay? And so this descent, this Montacci-Reutenauer descent is going to define a signed integer composition. So by signed, I mean my parts can be positive or negative. And I'm just going to show you how to do that with an example. Okay, so here are some permutations or elements of B2. So what is the Montacci-Reutenauer descent of this element? Well, I see that -1 and 2 do not have the same sign. So that tells me I have a descent at position 1. I draw a line where I have a descent, and I see that I have a piece of size 1 that's negative and a piece of size 1 that's positive. And so that tells me that my composition is going to be, let's call it a 1 bar if it's negative, and a 1 for positive. Okay. Next permutation. So this one, -2, -1 have the same sign, but if I take the absolute value, 2 is bigger than 1. So again, I have a descent at position 1. I draw a line here. And now I have a part that's negative and a part that's negative. And so my composition shape is going to be 1 bar, 1 bar. Okay. If I go to this next permutation, -1 and -2 have the same sign. But when I take their absolute value, 1 is less than 2. So that tells me that I actually have no descent. So I don't draw a bar. And now I just have a piece of this permutation that's size 2, and all the entries are negative. So that tells me that I have a composition, a negative composition of 2. Okay, and then lastly, this is the identity. There's no descents. And so now I have a part, one positive part just of size 1. Okay. Questions about this? Okay.
Sorry. So this statistic is not Eulerian, right? So it doesn't have the same distribution as the usual descent in type B.
No, it doesn't. Yeah, it's like a different descent.
Okay.
Completely, yeah. Yeah, like for example, there's 2 things that have no descent. Okay, so the theorem is that this is due to Montacci and Reutenauer, is that again I have a subalgebra, this time of the group algebra of Bn, that's generated by taking sums of elements that have the same composition type or shape. And I'll call that the Montacci-Reutenauer algebra. So here, for example, when n is 2, I have 6 signed compositions. Okay, here they are. And I'm summing over elements that have the same composition shape. Okay. Okay, and so again, we have this nice algebra. You can ask, can you define idempotents and decompose them? And Monica Bazzarani did. So she defined a family of complete orthogonal idempotents for this Montachi-Reitnauer algebra that I'm going to call G lambda. But now, because I'm dealing with signed permutations, my lambda is actually going to be indexed by double partitions. So these are two partitions whose size sums to n. Okay. And so again, I'm going to do the thing I did in type A, where I took this finer family of idempotents and I summed over them. So now I'm going to sum over G lambda, where the first there, so G lambda is indexed by signed partitions. I want the first part to be a fixed length. Okay. Okay. So again, that's going to give me now n+1 idempotents from 0 to n. And what you should think is that these G lambdas are generalizing my E lambdas, those by Garcia and Reitnauer, and these GKs are going to be my analog of the Eulerian idempotents. Okay, and I can actually be very precise about this relationship. So if I let tau be the map that goes from Bn to Sn by just forgetting the signs of permutation. So for example, if I have this signed permutation here, all I do is I just write everything positive. Okay. So Aguiar, Bergeron, and Nyman actually showed that tau defines an algebra homomorphism from the group algebra of Bn to the group algebra of Sn, and that when I restrict to, if I start with the Montachi-Reitnauer algebra, then what I get is a surjection onto the Solomon's descent algebra of the symmetric group. Okay, moreover, this map tau actually sends these idempotents GK to the Eulerian idempotents. Okay, and so the indexing is a little weird here because there's n+1 of these idempotents and n of these. So one goes to 0 and the rest go to match up with each other. Okay. So again, I'm gonna think about the representations generated by each idempotent by taking my idempotent and thinking about the ideal that it generates in the group algebra, okay? And so it's maybe a little bit less intuitive to see what these representations look like, but for example, in B2, so in general, Bn, irreducibles are indexed by double partitions. And in B2, here are my three representations. And I think this is difficult to see, but it turns out that this is also the regular representation of B2. Okay. So the reason that I am sort of bringing up these representations is that it turns out that they actually have a lift to Bn+1. So the sort of preview theorem is that for every k where my representations are defined, I can define some representation ik that restricts to gk, or in other words, I can find a lift of each of my gk's to ik. So again, this is a Bn rep, and this is a Bn+1 rep. Okay, and so I think again, as in the case of type A, sort of saying this gives you very little intuition, but what we're going to do is look at the topology, and hopefully that will give a little bit more intuition for why we actually have lifts in this case. Okay, so now I want to sort of find a type B analog for this topological story where I started with my configuration space of R3 and got a configuration space of this quotient. Okay, so in type B, the sort of right analog for a configuration space is called an orbit configuration space. So what this means is I'm going to have a group G acting freely on a space X, and I want to think about the set of points x1 through xn in X, where I now require that all of my orbits are distinct. So I'm going to give an example that I think makes this pretty clear. So let's let our group acting is going to be Z2, okay? And the space it's acting on is going to be SU2, so the sphere. And it's going to act via the antipodal action. So again, this is the wrong dimension, but what this is doing, what the antipodal action means is I'm taking like my north pole and sending it to my south pole, or more generally this point, I'm sending it to its opposite point. Okay, and so algebraically, that looks like P is sent to negative P in SU2. Okay, and so then when I form the Z2 orbit configuration space here, what I'm going to do is I take points P1 through Pn plus 1 in SU2, but now I require that Pi is not equal to plus or minus Pj. So this minus is really where that orbit configuration space is coming into play. Okay, and again, SU2 is going to act diagonally on this space. Okay, and I can think about typical, so I can form this quotient space here, and I can think about typical points in my space as being, okay, the set of points P1 through Pn, and now I'm going to say, okay, Pi is not equal to plus or minus Pj, so that's like this condition here, but then I also have to say also not equal to plus or minus 1, because this point is 1. Okay, so pictorially what this looks like is I'm saying, all right, I'm picking n points on the sphere, but I can't pick the South Pole or the North Pole. That's plus or minus 1. And if I pick this point, I can't also pick its antipode. Okay, so there's sort of more conditions. But again, we sort of have these two actions. We have our Bn plus 1 action on this space, which is, so my space still has n plus 1. It's an n plus 1 tuple, so I can act by Bn plus 1, and this is going to permute and negate now. So the negating is where we get our type B situation. And so this is going to be, you should think, preview of the lifts, which I called IK. And then we can also think about a restricted Bn action where I just permute and negate my first n coordinates and leave my last coordinate B. Okay, so this is like a preview of those GK representations. Okay, and so again, I want to relate this space. So in type A, I didn't have a Z2, but I had this quotient and I related it to the configuration space of R3. Now I want to take this space and relate it to some orbit configuration space of R3 that's not a quotient. And I want to do it in the same way that I did, which is via stereographic projection. Okay, so, but I have to be a little bit careful here because in type A, I was saying, oh, I'm picking endpoints on the sphere and I'm not allowed to pick the North Pole. That's okay because that's exactly the same thing as stereographic projection. Here, I'm saying, okay, I can't pick the North Pole or the South Pole. And so the South Pole under my projection maps to 0. So the first thing I have to be careful of is my point at 0 under the stereographic projection map has to be removed. But sort of more importantly, I have to be careful about my antipodal action. So over here, my antipodal action was very natural, right? It was just sending P to negative P. So like this point to that point. But once I stereographically project, things get a little bit weird. So in particular, the image of the antipodal action under the stereographic projection is going to send Q to negative Q over its magnitude. Okay, so again, this is another reason why we don't want 0 in our set of space. And okay, so it's a little bit weird, the action, but it's still a Z2 action on the space. And we still get sort of a very similar story. So this was our type A story. We had this homeomorphism between our quotient configuration space and our configuration space of R3. Okay, in type B, we have a Bn equivariant homeomorphism between this quotient orbit configuration space and our Z2 orbit configuration space, which I'm writing like this. So it's a set of points P1 through Pn. They're in R3, but not 0. And I'm requiring, okay, Pi can't be equal to Pj, and Pi can't be equal to this like weird antipodal action, which I'm going to call phi, just so we don't get it confused with like the sort of standard Z2 action of just negation. Okay, so I'm going to write this space like that. Okay, and to give you some intuition here for what that space looks like, in the case of, let's just say R, so this was, if you remember in type A, the sort of ordinary, if I got rid of this, the ordinary configuration space of R is the complement of the braid arrangement. You can see here that in this is the case that n is 2, this space looks like the complement of these curves now. Okay, so these ones are all lines, but then we have this very nonlinear restriction. So the points in my space are the points not on those orange curves. Okay, so it might seem like a strange space, but it was studied by Feichner and Ziegler in the context of studying orbit configurations on orbit configuration spaces of spheres. Again, we have that the cohomology is concentrated in degrees that are multiples of d-1. And we have a presentation that looks very similar to the type A configuration space presentation. So again, I don't want to like dwell on the details of this presentation, but it's sort of very reminiscent. And in particular, in the case that this D is odd, I again have that the total representation here is the regular representation of Bn. Okay, and so the theorem is that for every k where I have one of these representations, or where this cohomology ring is non-zero, I have a representation isomorphism of each piece of this, the cohomology of this orbit configuration space, with each representation coming from those idempotents in the Montachi-Roy-Naur algebra. Okay, and then this representation of Bn lifts to a Bn plus 1 representation where it's being described by the pieces, the cohomology of this quotient Z2 orbit configuration space. Okay, so I think I do not have time to talk about this, so I'm just going to skip it and give you the summary. So here's my type A story, where I had my Eulerian idempotents, my pieces of my configuration space cohomology, all lifting simultaneously to my Whitehouse representations, aka the pieces of this cohomology ring. And now we have a type B analog as well. So we have our representations coming from idempotents in the Montachi-Roy-Naur algebra being described by pieces of an orbit configuration space, and then lifting to a Bn plus 1 representation where they're described by pieces of this Z2 orbit configuration space quotient. Okay, thank you.
Let's thank the speaker. Okay, do we have any questions?
Can I ask a question?
Yeah.
Awesome talk. Thank you so much. I'm curious how far away this is from being from the same story in type D. I guess just I'm thinking from the arrangement perspective, you're forgetting the coordinate hyperplanes.
Yeah, I mean, I think that like, I think that it's possible, and I think that it would probably, you could take what's done here in type B and like interpret it for type D. I think that like you have to be careful about what space this is, because there's sort of the natural action on an orbit configuration space is a Reith product. And like type D is not that, so you might have to like do some work to figure out like what is the topological space happening over here. But I actually think that the Montachi-Roy-Naur algebra is defined for type D, but I don't know of any idempotent, like, so you kind of you'll have to do more work because a lot isn't developed in type D, but I think it's possible.
Sorry. Is Montachi-Roy-Naur in type D already defined somewhere? Or do you think it is easy to define it?
Sorry, say that again.
I didn't get what you say. You say that the Montachi-Roy-Naur in type D is already defined, or you think that it can be easily defined?
I think that it's already defined. I have to check on that, but I think that I think that it's already defined, but I'm not totally sure. If it's not defined, I think it would be possible to define.
Okay, thank you.
Mhm. Joseph, that's a great question. That's something that I have been or tried to do and have not thus far been able to, is to find some sort of idempotent like this. I think it should be possible, but I don't know how to do it yet. I sort of tried the thing that you would expect to general, like sort of the way that this is defined. I sort of tried what you would expect for type B and it didn't seem to work, but I think it should be possible. At least I hope so. Okay, so the question is there interesting stories for other group actions on the configuration space? So like on other configuration spaces?
Yeah, so now so in type A, you take like Z, we can say a Z1, and for type B, a Z2 as a group action. So if we take, let's say, a ZK or another group, is there any known story about that?
I don't know. I think that there should be. So like there's like the natural group candidate in that case would be the Reith product. It would be like, it's sometimes written as like GR1N, which is the Reith product of ZR with SN. And this is like a shepherd group. And I think that there should be some sort of story in that case, like maybe generalizing at least part of this, if not all of it. Again, I think that like there's some sort of, I think the tricky part might be that like over in the topological world, like we were using the fact that we were looking at the configuration space on R3, like we really needed it to be odd. And once you move to like a complex reflection group, or like if you were thinking about like a ZR configuration space, you would sort of have to get roots of unity in there. And so then you're starting to think about complex space. And so then you kind of lose this odd dimension. Like it kind of becomes even. But I still think this is something that like I've wanted to sort of work on in general. I still think that there should be some sort of story here, but I'm not exactly sure what it should be.
Thank you.
Good question.
Sarah, about your comment about the IN minus K.
Yeah.
I think it's true. I'm trying to remember. But if you take your lift and tensor it with the reflection representation, then you'll get the Eulerian idempotent one up. Like you take your lift, which is an SN+1 representation, and tensor it with the reflection representation, and that should give you the Eulerian representation, the corresponding Eulerian for SN+1.
Right. Yes. Yeah.
So have you tried doing that same thing here?
Yes. So I actually do. Yeah, there's sort of two properties of these lifts that I didn't really talk about, or actually a couple, but two of them that you might be interested in are one, yeah, we have some sort of like recursion type formulation, where instead of it being the reflection representation, it's like a sum of two irreducible like BN representations. I think they're like, one of them is the reflection representation and one of them is something else. And yeah, so you can get at like what these representations are sort of recursively if you know these representations. And then the other property is that like the total, so like when you sum up all of these representations, the total representation is like that induced representation from like the cyclic group, the trivial representation. In this case, if you sum up all of these representations, the total representation is the like induced from the cyclic group generated by a Coxeter element.
Okay. Thank you.
Yeah.
Very
good.
nice.
Thanks.
Okay, I think we're gonna cut the official question period here. It's already getting kind of late, so let's all thank Sarah again.
Yeah, sorry, I went over.
You had lots of questions.